Hello everyone, good evening. Please let me know if I'm audible to everyone. You can type it in the chat box. Good evening everyone. Please let me know if I'm audible to everyone. You can type it in the chat box.
You are audible, Charlotte.
All right. I will start with a quick introduction in the next 2 minutes, and then we will begin the session. Hello everyone, and welcome to another session of the Academy Series at Formula Bharat. Today's topic is Introduction to Computational Electromagnetics and its application to automobiles. And this will be presented by Hara Prasad Sivala and Manisha Kamal Konda, Senior Application Engineers at Ansys, who are our knowledge partners. CEM plays a prominent role in developing and understanding reliability of race cars. This session will enlighten you on the fundamentals of electromagnetics and governing equations. Also learn how to apply electromagnetics to design high-efficiency motors and highly reliable, high-speed electronic systems inside automobiles. Without wasting any time, let's start the session and learn more about the applications of CEM on automobiles. Manisha, over to you.
Yes, Charlotte. Thank you for the opportunity. So I would like to share my screen. Please let me know if it is visible.
Sure. Yes, it is visible.
So hello everyone, good evening. So I'm going to discuss on this introduction of computational electromagnetics and its application in automobiles. The agenda would be introduction to computational electromagnetics and the governing equations, and how electromagnetics is useful in automobile industry. Computational electromagnetics is just like modeling, is a process of modeling the interaction of electromagnetics with the physical objects and the environment. It's just like uses the Maxwell equations, either in a time domain or frequency domain format, either in the integral or differential or integral form, and perform these operations on the existing structure, which is which can be a CAD geometry, for example, or a electronic PCB. So in that case, Maxwell equations are applied on this structure, and both electric and magnetic field will be calculated out of the structure. So this is basically how computational electromagnetics work, and the advantage of this computational electromagnetics is basically we can reduce the effort taken for experimentation and reduce the cost incurred. So some of the advantages of computational electromagnetics in a technical side would be simulation of the entire structure, and the engineer or the user can understand the fields and resonant modes in that are occurring in that structure. And simulation of, for example, a PCB is using, he can he can simulate the PCB, and by simulating this PCB, you can understand the quality of signals, that is the quality of the signal that is driving the ICs, and quality of power that is supplied to the ICs. So basically, quality of this power and signal is very important for better performance of these ICs. Hence, simulation of this PCBs, any electronic PCBs, is needed. And to understand the electromagnetic compatibility, which is another important area which any electronic item need to be taken care of and need to be compatible in terms of electromagnetic radiations or emissions. Also, to understand this whole understanding the quality of the signal and quality of the power and electromagnetic compatibility, to this everything comes under the electrical reliability. So this helps to understand this computational electromagnetics helps to understand electrical reliability of the structure. Also, these outputs obtained from this analysis can be useful to perform the thermal analysis as well. And this thermal analysis, taking the inputs from computational electromagnetics, is important because it helps us understand how these fields or currents that are flowing in a PCB or any structure can help to understand how much temperature it is generating, and thereby understand where the heat is concentrated in that particular structure or a PCB, and thereby take a necessary action to perform to cool the circuit, and also thereby improve the thermal behavior or thermal reliability of this PCB or a structure. Also, this thermal how electronics and thermal are interrelated. Similarly, thermal due to continuous heating and cooling of this structure can impact the thermal structural reliability of the PCB. So hence, computational electromagnetics, the output of this CEM can be useful in understanding not only the electrical reliability, but also to understand the thermal reliability and structural reliability as well. So some of the advantages in non-technical aspect would be like it can be cost effective. It can complement the analytical and experimental electromagnetic testing, where we need a large chambers or a test bench setup to perform this electromagnetic testing. So that can be avoided when you are using or going for this simulations, which consider the numerical approach to understand or compute the electromagnetic behavior of the structure, and also less time when compared to experimental setup and experimental based approach, and capability to simulate the fields that are not possible to replicate in experiments. So one can understand the fields that can how much electric field or magnetic field is actually flowing on the structure, which cannot be possible in a physical experiment. And also one can perform mathematical operations on this on the results that you get, and understand and use it for further analysis purpose. Ability to solve complex electromagnetic fields, unlike analytical approach, and detailed visualization of these fields is also important to understand how this structure is behaving. Also, comprehensive information on the field behavior. So every information we can collect, and we can perform the mathematical operations on these results for the further analysis. So some of the limitations of this computational electromagnetics can be, this is just an alternative for the, this is just an alternative, but it cannot actually replace the physical experiments, because physical data is necessary for any electronic component or any system to get into the market, and dependent on experimental data for validating. Sometimes the models need experimental data to perform certain simulations as well. So in that case, experimenting is necessary. Also, some of the errors that can occur in computational electromagnetics due to round-off error or iteration error or a discretization error or a model error. So hence, this cannot be completely accurate, but it can be, this accuracy can be depending on the type of approach we choose to analyze the structure. Actually, limited to EM based simulation and doesn't consider EM effects. So this point tells about, like, in terms of HFSS, like it basically deals with electromagnetic behavior of the structure, but it doesn't accommodate other effects, like for example acoustics or vibration. So that effects cannot be taken into the simulation, and that effects cannot be considered. So simulation of such structures is not possible in case of electromagnetics, where in CEM only electromagnetic behavior is considered, and other effects cannot be considered. So that can be one limitation. And also another limitation would be a hardware computer, where depending upon the structure, you need to have a better RAM. You might need a better RAM, higher memory to actually simulate that structure. So some of the applications for computational electromagnetics and field of operation would be, so in case of aerospace or defense or automobile applications, there a PCB is necessary to mount any electronic component. So hence the PCB reliability is necessary. And in aerospace and defense, radar is necessary to detect the targets, and hence radar simulation can be important. Antenna and array design is also one of the major applications in automobile and defense area. And because of the presence of lots of electronic systems, and these need to be integrated, cable is necessary, and hence cable modeling and harnessing of the cable in terms of electromagnetic compatibility. So cable harnessing and modeling of cables is also necessary. Also, one need to take care of electromagnetic compatibility, which is a very important area, where every electronic component has to undergo this EMI/EMC testing to get into the market. So another applications would be in the field of radar and RF antennas, and RF circuit and radar simulation is one of the field of operations. And consumer electronics, in consumer electronics, PCB is necessary to mount any electronics, so hence PCB reliability is necessary. And at the same time, EMI/EMC compliance is also necessary, because consumer electronics are used everywhere, and working of one electronic system should not interfere with the another system. So taking this into consideration, electromagnetic compatibility is necessary. And in terms of IoT and networking, in this as well, the PCB and antennas and EMI/EMC is necessary. And in terms of electrification, so PCB and EMI/EMC is necessary. So future of electromagnetics would be rapid computational power and reliable and improved. So the numerical methods are being improved day by day, and there's a lot of scope in computational electromagnetics, and adaptive meshing algorithms are getting improved day by day. So this reduces the this improves the accuracy of the simulation, and also reducing the time taken for simulation. So the customers might be more interested in such kind of simulations where we can get the much accurate results within less time. So also the simulation tools are improving day by day, and hence they can overcome the previous limitations that are mentioned now, and also able to meet the critical customer applications. Basically, computational electromagnetics deals with Maxwell equations. Maxwell equations here are listed below, like both electric and magnetic fields. These Maxwell equations tell how this electromagnetic behavior of this electric and magnetic fields. So the curl of electric field is creating a magnetic field over here, and the curl of magnetic field is creating an electric field over here. So D is nothing but epsilon into E, and B is nothing but mu into H. So a time varying behavior of one field is creating the another field. So this causes the four equations exactly define how the electromagnetic field is behaving when it is flowing through air or any other structure. So there are different forms of this electromagnetic of this Maxwell equations. One is time domain and frequency domain, where we have we have a differential and integral forms. So these corresponding equations can be chosen based on the application, or based on the structure, and thereby compute these Maxwell equations and obtain the E and H fields of the corresponding structure. So that is the idea behind using the Maxwell equations in computational electromagnetics. If we check with the different tools, so basically HFSS, SI wave, Maxwell uses a frequency domain differential form, and some of the other well-known tools like Numerical, they go with FDTD is another technique, and even in HFSS there is a transient HFSS transient. You can use a time domain method, time domain form of electromagnetic Maxwell equations. So basically, it depends upon what structure you are choosing and what application you are choosing, and based on that criteria, you can select the tool itself selects which form of equations is useful, and which form of equations can give more accurate results within less time. So the governing equations of electromagnetics, so basically Maxwell equations. Basically, electromagnetic equations, Maxwell equations are the governing equations in any computational electromagnetics. And here, if we check with HFSS or SI wave, it is based on the finite element method. So finite element method is nothing but is basically dividing the structure into finite number of tetrahedrons in case of volume. I mean, in case of let us say any structure, and triangles in terms of planar structures. Tetrahedrons in terms in case of volumetric structures, and triangles in case of surface structures. So this we call it as mesh. So discretizing, I mean, dividing the entire structure into smaller forms. We call it as mesh. And the governing equations is, so the Maxwell equations, when deduced, we can get when we are actually substituting h in E in terms of h and one h in terms of E, we get this equation and we can deduce this equation. And this is the equation, we call it as a second order Maxwell equation, that is useful in computational electromagnetics. This is the equation that is being used. And so if we simplify this equation, we get L into E, which is basically here everything is linear. So the curl is a linear function, and this one is linear function, and we can actually take the E as common, electric field as common, and we can replace the entire equation with L, and this will be equal to some function F. So what happens in any electromagnetic in any computational electromagnetic tool is, so E is represented in terms of some basis functions, and this basis function will be weighed according to the so the electric field here is a function of basis function. So this alpha we need to calculate, and this alpha, when this alpha so we can get different values of this alpha, and we need to choose the tool itself chooses the correct value of alpha, so that based on the meshing criteria, alpha value will be chosen, and this E is can be L into E. So this E is mentioned as tilde because of its because we are actually approximating the fields, which this is not the actual field, but it is approximating, and when it reaches 0, then we can say it is converged, but practically it doesn't happen. So always in practical situation, there is some finite value of R. So this R, this is for single domain, single mesh, and we integrate it over the entire geometry. So which is nothing but when we deduce this, we can replace this as a into x equal to b. This kind of matrix we can obtain. So where A is, again, if we replace R with all the equations that is mentioned, so this will be the matrix equation. This will be the entire equation for A. So by solving these equations, we get some fields, and that fields is nothing but electromagnetic fields, and from that field is electric field, and from electric field we deduce a magnetic field again from the Maxwell equations. This is how computational electromagnetic fields work in any simulation. So basically, in order to so the setup procedure for simulation would be create a geometry, generate a mesh, and material selection, and define a boundary conditions, and then based on we import some ECAD or MCAD, which is nothing but MCAD is mechanical geometry and ECAD is electronic geometry. So we import this geometry into the tool, and based on the initialization and I mean initializing the frequency setup and convergence criteria, the solver solves the structure and obtain S parameters or fields or surface currents or field radiation field. So this is the procedure for computational electromagnetics setup. How to set up the structure for simulation. So electromagnetics can be divided into two types, a low frequency and a high frequency. And in case of high frequency, there are again divided into two criteria. One is near field and one is far field. So near field, we can say based on the based on the distance from the antenna. So and at near field, there are what we call two theories can occur, like one is coupling and one is crosstalk. In coupling can be advantageous when we are actually designing a coupler, or when we want the structure, when we want the electromagnetic field in one line want to couple to the another line. So based on that application, that can be either advantage or disadvantage to us. So here, if you are designing a coupler, then it will be advantageous to have a coupling. When we are designing some another, when we are using for some other application, say just a transmission line, and you don't want any coupling, in that case, near field can actually cause a crosstalk, where if two lines are nearby, very close by, so the fields in one line can actually interfere with the fields in another line. So in that case, it would be a crosstalk, and this is not recommended, and we need to avoid the crosstalk in such cases. And in another other criteria would be far field. So in far field, when we have we have both radiation and emission. Radiation is again advantageous when you are designing. In case of antenna, radiation would be advantageous, but when you are designing something which should not radiate, and in that case also radiation is happening, that is again a problem. So in that case, you need to again take care by redesigning the entire structure or entire PCB. This slide tells about meshing and solution process. So as mentioned previously, so you just need to import the geometry, and the tool will initialize a mesh, or we can or the user can also initialize a mesh depending upon the depending upon his expertise, or depending upon the type of accuracy he wants, or depending upon other factors as well. So initial mesh is defined by the tool itself. So, and based on this flow chart, the entire structure will be refined, and would create a refined mesh, and we can obtain some fields. So here in this case, S parameters. So this is a convergence criteria. This convergence criteria, how it is met. So that is basically, so initial mesh is created, and again, when you create a mesh, so the tool actually solves for electric fields. So when this electric field is solved, and when it checks whether the convergence is matched. If it doesn't match, it again remeshes to a finer mesh, and again solves the entire geometry based on that mesh. So this process repeats, and when the solution criteria is met, then the obtained results would be accurate. So this is advantage when this is advantageous to the user, because user need not actually concentrate on the meshing, but he can actually concentrate on the geometry. So some of the equations, some of the methods that are followed when deriving this Maxwell equations is direct and iterative methods. Direct method is just as mentioned, like Ax equal to B, and solving that x in that equation by a matrix form. And iterative method is by taking the by taking certain iterations or some certain numerical equations to solve in form of in several steps. So depending upon the structure and application, the customer or the user or the engineer can choose which method is suitable. And also user can choose which solver to be used. So here we have different structures. This can be a very small structures ranging from centimeters or millimeters to bigger structures ranging to kilometers. So in such structures, the customer has the user has the ability, user has a choice to choose between which type of solver to use. So as mentioned, like different solvers use different kind of Maxwell equations, and based on the structure or based on the application, the user can choose the corresponding solver, and thereby the solver at the back end, it chooses corresponding Maxwell equations. So in terms of for automobiles, the computational electromagnetics is important because the automotive electronics are present in all the automobiles. So this these electronics are again mounted on a PCB, and so in that case, signal the problems at PCB and cable level may affect the functionality of the system, and results can be very catastrophic. So in such cases, one need to address signal integrity, power integrity, and electromagnetic interference, and electronics cooling and structural reliability. These all are important aspects to look into when you are dealing with the electronics in any automobile. So as mentioned previously, so computational electromagnetics tool has several advantages, like reduces the development cycle, or understanding the fields on the PCB, optimizing the components, optimizing the electronic components, electronic structure, and improving the reliability. So some of the factors affecting the electronics reliability would be, so improper PCB design is one of the main factor that affects the reliability of the structure. So the engineer or the user can design may have designed the PCB without following certain guidelines. So in that case, this could affect the overall reliability of the entire electronics, and results can be very damaging. So in that case, so some of the mistakes that are highlighted over here. So one is common impedance loop coupling. So here we see a here the figure tells, like he's using a same return path for both the loops. So this current will be looping back over this return path, and again the other current I1 will also be looping back into the same path. So in that case, due to this, a voltage will be created along this because of the finite resistance over that cable, over that wire. So in that case, a voltage can be induced, and this can couple with the nearby mesh. So in that cases, this could act like a radiator, and this loop can be a victim, and the current inside this loop may change. So because of this, currents are actually changing within the circuit, and which is not expected, and which can result in the current change in the entire structure, entire system as well. And another factor could be differential and common mode coupling. So where we have differential mode is nothing but current is flowing in different directions. With this over here the current is flowing in one direction, and over here the current is actually flowing in another direction. So what we assume is generally this currents, because flowing in opposite direction, we assume that currents at certain the fields at certain distance will actually cancel, but it doesn't cancel as that, because the distance from this wire to the observation point and distance from this wire to the observation point is different. So they don't exactly cancel, but the fields can be reduced. But this field also has an impact on the reliability of this of any electronics. So in that case, this is actually equation that that can be used to understand that mathematically. So the possible solution would be to reduce the loop area. So instead of routing this to over a larger area, you can just route it over the small area. So just a straight line for the transmission path and return path would reduce this problem. And one more effect is common mode coupling. So here we have two lines which are flowing in same direction, and in that case also the currents interfere, and I mean the fields interfere, and which cause constructive interferences, and which result in high electric fields. So here this will act like a this line will act like somewhat like a radiator or an antenna. So in that case, the possible solution would be to reduce the size of this line. So this can be one of the factors that can be affecting the electronic reliability, and the user might not know this kind of what kind of approach need to be taken to overcome this problem, and directly go with the simulation, go with the structure, and implement it in the automobile, and that could be less reliable. So the entire system would be less reliable. So another effect is capacitive and inductive effect, where the two transmission lines are very close to each other, and this fringing fields can actually couple to the nearby line. And in this case, this is the current flowing in one wire can actually interfere with the loop that is present nearby. So such kind of practices need to be avoided to design a most reliable electronic component. So, and another effect is parasitic effects of the capacitor. So here we have in this capacitor we have one with a shorter lead and another with a longer lead. So this can be because of this difference in lengths could give rise to a different kind of impedance value, so which behaves like a capacitor at certain frequencies and like an inductor at some certain other frequencies. So in that case, the user need to take care while dealing with such kind of designs. So this is not only with the capacitor but with every lumped component like R, L, and C as well. Another important field, that is electromagnetic interference. So here we have a electronic system, and which have a power lines and signal lines. So this system, when working, due to presence of high speed switches inside this component, and running at different frequencies. So these frequencies can actually affect the signal that is flowing into the power lines, and causes the noise. And this noise, when this same power lines are connected to every other component as well within the within a system. So in that case, so the noise from this noise generated inside this system is actually traveling to the entire system, entire other systems as well. So in that case, this we call it as a conducted emission, and this need to be overcome. And again, the signals, the signal lines that are coming out of this case can also act like an antenna and radiate. So this radiations can couple to the nearby system or a nearby electronics that are present close to this structure, close to this system, and can also affect their performance. So this we call it as a radiated emissions. So an electronic component need to be designed in such a way that it radiates less, or it creates emissions less, both radiated emissions and conducted emissions, and need to be able to immune with respect to both the conducted and conducted and radiated emissions. So immunity in the sense, like just like this system is radiating and creating emissions, the nearby system may also be radiating both in radiation, both in air and as well as in conducted parts. So in that case, this system need to be immune to the system need to be immune to such kind of radiation. So the system need to be designed in such a case. So so this kind of analysis simulation, I mean, computational electromagnetic simulation would be useful to understand this kind of radiations and emissions, and thereby engineer or the user can take care accordingly. So another aspect would be PCB reliability, where electronic, so we discussed till now as signal integrity and power integrity, and which is nothing but electrical reliability. And this flow of currents will cause the will generate the temperature, and this temperature can be so this temperature can actually affect the reliability of the system as well. So in such cases, the thermal analysis need to be performed, and at the same time, due to continuous heating and cooling, the mechanical reliability can also be degraded. So all this reliability check can be performed based on the results of computational electromagnetics, like E and H fields. So this tells about the computational electromagnetics, how it is coupling with the temperature, and we can and this tells about how computational electromagnetics, which leads to temperature changes, is actually affecting the reliability of the structural reliability of the PCB. So by this, I would like to conclude that by careful design of electronics, electronics inside an automobile. Basically, because of the closely packed electronics units or random vibration due to mobility of the vehicle or heating problems. Due to this all problems, electronics inside the automobile need to be designed very carefully, and computational electromagnetics is useful in analyzing and simulating that structures. Charlotte, over to you. Thank you, everyone. You can take the questions. Yes.
Thank you, Manisha. Now we'll have Hara Prasad presenting. Hara Prasad, over to you.
Hey, Charlotte, thanks for this. May I know how much time I have? Are we running out of time?
So the session was supposed to be from 6 to 7 p.m. But yes, you can go ahead with your presentation right now.
Great. Maybe I will try to sort it out. Okay, that's not an issue.
Sure. Thank you.
Great. Thanks. Hey, thanks, Manisha. Thanks for the nice presentation, and it's so elaborated one. Great. I hope I'm audible and you guys are able to see my screen. Could you please confirm that?
Yes. You're audible and we are able to see your screen as well.
Great. Thanks for that. So welcome to Formula Bharat Academy Series, and myself Hara Prasad Sivala. And today's topic would be on the introduction of CEM and its applications on the automobiles. So of course you guys have already gone through that, a couple of topics on the CEM front, but you might see a bit difference from the high frequency to the low frequency. Of course, there might be some slides which are overlapping, but I will rush through those things. Okay, that's fine. So here is a simple agenda. We will just go through the introduction of CEM and what exactly is CEM and what are the advantages and limitations. Okay, a couple of things on that front, and which is followed by the governing equations, which talks about the Maxwell part and a couple of basic laws also. Along with that, what is the difference which you can see from HF to LF, and finally what would be the automobile applications. Okay, so that's the overall agenda. Of course, if you want to talk about CEM, I think we need to see these phases. Okay, that's the point. So I no need to explain these things. Michael Faraday and James Clerk Maxwell. So whoever is working on the electromagnetics, those should know these phases. Okay, that is the first thing. And when we talk about the electromagnetism, basically it's combined of two words. Okay, the electricity and magnetism, which are different facets of electromagnetism generally. Okay, so if you want to, in a nutshell, if you want to tell this, when there is a moving electric charge, that will help you to produce the magnetic fields, and when there is a change in magnetic field, that will help you to produce this electric charges. So that's a simple connection between these two, and these two guys have have identified this particular phenomena. So that's a beauty, and that's where we are living with this electromagnetism things. So if you want to understand this electromagnetism, okay, so we have an option. This is where the science comes into the picture, like computational electromagnetics. So it generally talks about how this electrical fields or electrical behaviors of interacting with the nearby components, okay, or the physical objects which are nearby, and how it is dealing with that particular scenarios. So that is, we basically call it as a computational electromagnetics, and how we are handling that. And whereas to handle these things or to understand these things, generally the basic laws which comes into picture is the Faraday's law, which talks about the induction part, and the Gauss law for magnetism, and even the Ampere's law and the Gauss law for electricity. So these are the basic laws which deals with this complete electromagnetism part. And when you say this computational electromagnetism, of course, it's not a complete replication of the experimentation, but it's it's complementing this part. Actually, the testing, it can be the experimenting, so that is a complementation of that. So we'll see computational flow electromagnetics part. So when you say this electromagnetics, to handle these things, there are multiple ways to do this. Okay, the basic way is like analytical, okay, which came which comes from long back, and whereas the other one is like the experimental, which many people in the industry are following this. And on the other side, this computational electromagnetics, which deals with, of course, it also involves the computer aided things, where it deals with both of these things. Okay, it can help you to reduce the time which you're spending on this part, or it can also mitigate a couple of challenges as well. So that's where this computational electromagnetics will help you out. So of course my colleague Manisha has already run through these things, advantages of these things. Just I will give a brief overview on that. So as I said, this experimental data or analyticals, okay, can be reduced a bit. Of course, you no need to do all those experiments or analytical calculations or experimental things, whatever you're doing when you are jumping to the computational electromagnetics, because this computational electromagnetics will gives you a digital twin of that. So you can able to replicate your product using this particular electromagnetics, computational electromagnetics, and which is cost effective because it automatically reduces the material which you are putting in the physical prototyping, or the amount of time which you are spending on the experimental physical testing. So that will be reduces, and the less time to compare to the experimental. That's obviously true. When you are reducing the number of physical testings, then automatically it will reduce the amount of time you are spending on that part. And ability to solve the complex electrical and magnetic. Okay, the reason why we said is like, in few cases you might not able to see the same thing even you are running the physical in your physical testing also, but those things can be replicated in the in the simulation point of view or the computational electromagnetics point of view, and we can able to visualize those effects that you can't able to see it in a real-time experimental scenarios. And the remaining advantages which we already come across, the capability to simulate electromagnetic behaviors that is which are difficult, which you can't able to do I can say cost effective, which means that if you are going for a some of the particular experiments which is very cost effective, I can say that you can't able to really go for a physical testing, like a short circuit cases and a huge transformers or anyway that kind of scenarios. You can't, it's really difficult to build that. So that's where this simulation can help you out to reduce those experimental things and the cost which which was involved in that particular analysis part. And of course the next part would be like the complete comprehensive multiphysics analysis, which can help you out to do the multiple analysis on these electromagnetic devices. And the limitations which my colleague has already mentioned, first thing is like, of course you might do a lot of analysis on the computational electromagnetic side, but this is not a replication of the physical testing. Even you do the digital twin, or even you do many analysis types on the electromagnetic components, but still you have to do the physical testing at least at least once for the particular prototype. So that is one limitation. And the next part is the dependent on the experimental data, which means that you might have a computational electromagnetics part, but the thing is, unless until you validate a particular product or anything, you don't know that whether how accurate it is with the physical data or anything. So that's where at least once you have to validate that particular one, so then only you can able to trust that particular solvers, whatever it is. And when you're working with this kind of solvers, what happens basically, it deals with a lot of I can say environments, which deals with couple of errors. I can say it can be the numerical error or iterative error when you're going for a mesh convergence or anything, and the discretization error. Okay, and when you have some overlappings in the geometries or anything, then you might not get a proper mesh and it might not converge. Okay, so that's where this discretization or the mesh errors will come. And the overall model error, a model error, like how exactly the geometry has to be there, that has to be taken care. Otherwise you will get this kind of geometrical error as well. Okay, so these are all comes when you are going for a computation of this particular electromagnetic components. Okay, and along with these things, as I said, when there is when the size of the model is getting increasing, obviously the amount of hardware which you are which was required by that is also be is also to be increases. So that's where we should be very careful, like how good is how good is the how big is the problem and what sort of hardware is required for that. So that is also one of the limitations. It has to be improved to reduce the simulation time. And couple of applications, I just give you a brief on this part. One is like, by using this computational electromagnetics, whatever the sort of application it is, it can be a static, steady state, or a dynamic component can be able to replicate. And you can also deal with a linear or a non-linear materials can also be possible. And you can also model some sort of advanced things. When I say advanced things, if your materials are in a varies with respect to the different directions, that can also be replicated. Okay, that we call it as advanced material modeling things. And it automatically improves the product quality and optimized product, which means that it optimizes the product and it reduces the amount of material which is required to build that particular electromagnetic device. And at the same time, it will shorten the development cycles. That is one thing. And I'm sorry, the complete product development cycle is going to be reduces. That is one good part with the computational electromagnetics part. And apart from these things, when you talk about specific to a particular applications, what exactly you can able to extract is, if you want to see the electromagnetic forces or the losses which you are getting out of this electromagnetic components, so such kind of electromagnetic outcomes you can able to predict by using this computational electromagnetics without any physical testing. Okay, you can able to extract those things. And of course, apart from these generic things, a couple of advanced effects like a demagnetizing effect. For example, if there is a permanent magnet machine, if you want to see a demagnetizing effect, can be do it without any experimental testings. And you can also predict that how good is the structural part of the particular machines, because whatever we are handling here, it's electromagnetic devices, okay, which are, I can say it's electromechanical, or we can also call it as electromagnetic devices, so which also deals with structural vibrations. So that how you can able to handle it. So this computational electromagnetics combined with the structural simulations or the computational fluid dynamics can able to address this thermal as well as the structural behavior of the problems. And here is a few, I can say very few applications or industries which I have mentioned. Aerospace and defense, where you can see a lot of actuators. It can be the solenoids or even the electromechanical components or electromagnetic devices. Okay, degaussing effects, it can be. So such kind of things you can also see, and even the motor side if you want. And the automotive industry nowadays, it's a booming topic, I can say, the traction motor, and even couple of other applications like it can be the bus bars which are equipped in this particular vehicles. Nearby the PCB components are like that. And in other scenarios, like if you also see something on the PCB front also can be doable. Okay, and home appliances, I can say, starting from a ceiling fan, you can also go for a mixers, grinders, any sort of things you can name it. And power generation and transmission, that is shows, I can say, potentials here to implement the component level simulations or a computational electromagnetics. And the industrial purpose, like you can see wherever we go, we will see the motor part. So that is, we can say, the booming area where a lot of people are changing from the mechanical devices to the mechatronic devices. That's where they need this electromechanical components or electromagnetic components, which deals any component which runs with respect to the electrical excitations. So that's where this mechatronics comes into the picture, and it's ruling this particular scenarios or current scenarios, I can say. And the future topic would be like whatever the the decreasing whatever the hardware is required for that, how you can reduce that particular hardware things, how we can able to reduce the amount of hardware which is required to solve these components. And the computational power has to be reduced. That's what we are mentioning part. And the reliability of these things, okay, and how exactly you can correlate these things with the physical testing things also, because some of the times people will do the physical testings in a different manner. So how you can able to replicate your products with the physical testing part also? Can we also include this computational electromagnetics and with respect to the physical testing scenarios as well? Okay, so that is I can say the future concept which might improve in the computational electromagnetics. And the one more is like integrating with the multi-physics simulations, and at the same time integrating this computational electromagnetic components in the overall system. So that is, I can say, the future concepts which can talk on this computational electromagnetics. So that's basics on that front. And the governing equations, I can say, as my colleague has mentioned, okay, so these are the 4 equations which talks about the complete electromagnetic theory. But before jumping into this, first we need to understand that what exactly these notations are. This is really difficult to understand. Okay, so that's where this curl or a divergence, okay, that plays a role, okay, which automatically simplifies this equation. So generally, if you want to define the divergence, what it states for is like the tendency of a fluid. When generally, to understand these things in a simple manner, they will correlate with the fluid behavior. Okay, so how the tendency of this fluid to collect at a point, okay, whether it's a dispersing or a collecting at that particular point, that generally defines the divergence of a particular component. Whereas this curl will define the swelling, how measure to tendency of this particular fluid to swell at that particular point. So that generally defines this curl of the particular, this particular component. So that is the basic idea. And if you talk about this Faraday's laws of induction, okay, generally this Maxwell equations are extensions of this basic equation which was given by the Faraday's or Gauss or Ampere's. Okay, so if you see the Maxwell, I can say the Maxwell form of Faraday's law. Okay, it states that whenever there is a change in magnetic field, which deals with the electric field, okay, which is responsible to produce the electric field intensity. So that is the basic idea. Okay, and whereas in the case of Gauss law for magnetism, it clearly states that I'm sorry. In the case of electrical, for example, I will get back to the Gauss law for magnetism. In the case of Gauss law for electricity, you can see the amount of the charge which was captured, okay, which is equal to the enclosed part, okay, whatever the charge which was enclosed in that particular surface or in the closed and enclosed surface, which the same thing will not be replicated in the magnetism. Because if you talk about Gauss law for electricity, in the electricity there is a we can say there is a monopole exist, like a positive charge and a negative charge, and always there is a charge flow from one charge positive to the negative or negative to charge negative is going to be like that. It is going to happen, whereas the same thing will not happen in the magnetism, because it is always there is a dipole. There is no monopole exist in the magnetism part, so it always forms a closed loop. There is no starting and there is no ending for that. So the amount of charge which was flowing through a particular closed and enclosed surface is zero. So that's what the Gauss law for magnetism is stating that. And when you come back to the Ampere's law, generally what Ampere's law states for is, whenever there is a current carrying conductor which will produce the magnet, or the magnetic field, this is what happening. But then extensive of Ampere's law is states for the Maxwell's version of Ampere's law. Okay, that's the stands for this partial derivative of the this displacement current. Generally, this is nothing but the change in electric field. The change in electric field in the Maxwell terms, they call it as a displacement current. So the displacement current is also responsible for the getting the magnetic field. So that's what this extension of this Maxwell's equation of the Ampere's. So these basic equations will tell us about the complete electromagnetism part, and we will jump into the basic class. I can say that's what, as I said in the previous case, whenever there is a change in magnetic field, which will responsible for the electric current. Okay, so that's what they are doing here. If you can look at this, images, they are going with a permanent magnets, or it can be an electromagnet or a sudden switching. So all those things, which states generally defines the Faraday's laws of inductions. And on the other case, you can see this is the Ampere's part, where when there is a current flowing through a particular conductor, then how the magnetic field is going to be produced. And here is a different scenario when you are taking a couple of coils, okay, which are twisted around it, and when you are pumping some current through that particular coil, then how it is going to behave? It's behave just like an electromagnet, okay. And at the same time, if there is a steel material or anything, if you are putting inside of that particular coil, it behaves like an electromagnet, okay. So that is also there. But apart from the electromagnet, once you remove the supply, again it will behave its original property. Of course, it might have some residuals, but on a holistic sense, it is generally an electromagnet. Once you remove the electricity, it automatically behaves like a general steel component. Whereas the permanent magnet, it has a permanent magnetic field, which automatically works whether you are giving an external supply or not. It doesn't matter with that. It always behaves like a permanent magnet, which carries the magnetic field in that by default. So these are all like general electromagnetic theory, but honestly speaking, to understand these things, there are something has to be there. That's where, as I said in the initial slides, there are analytical and experimental data, and then computational electromagnetics. But to address this part, we have in a simple format, there's two techniques, like analytical or numerical. So in the numerical, again, because I will also come like why we are not going for the analytical, because few things you might not able to replicate with the equations, which we do not have it actually for the complex structures. Okay, for some of the standard components, yes, definitely we have it. But whereas in the case of some complex structures, it is difficult to go with analytical equations. No one has defined an analytical equation for that. So that's where this numerical techniques is help you out. And it has multiple formats. In that, integral and differential equations as a one. And again, according to the form of how they are interpreting those things, there are multiple techniques like boundary elements, BEM methodology we call it as, and FEM, finite differential method, and finite element method. Okay, so out of all these things, most of this electromagnetic solvers as defined on the finite element method, which is much more accurate because it will do the integration part of it. Okay, where it will compute the fields at each and every point, whereas the finite differential method is like a kind of averaging the things, so which we might lose an accuracy in that particular sense. So this, to understand all sort of applications, because when you talk about those 4 basic equations, there are static equations and there are also the dynamic equations. So to understand those things, so any solver has to provide this 6 set of solvers. Okay, those are like static applications, electrostatic and magnetostatic, and the steady state fields, or we can also call it as a eddy current, and the AC and DC conduction. Okay, when there is an AC and DC on the electric point of view, like how it is going to behave. And on the other side, the transient in both electrical and magnetic fields, how it is going to interpret those dynamic behavior of a component. So those are all can be handled in a multiple, I can say in a multiple solvers. Okay, whatever the solver you might choose it, that has to understand this particular behaviors. And the good part is, few applications can also be replicated in a 2D environment, or few applications has to be replicated in a 3D. It depends on application to application. Okay, so that's generally the solver point of view. But as I said, always when you go for a computational electromagnetics, the base of this one is the finite element method, which generally talks about the number of mesh elements. So in the case of electromagnetics, it's not like a computational fluid dynamics or a structural analysis part where you should have a dense mesh at a particular area and you should have a coarse mesh. Okay, I mean you should have an equal proportion of mesh at each and every area, and those many elements is not required in the case of electromagnetics, because how it's going to be deal with is wherever there is a higher field gradients, there we will need a dense mesh, and wherever the fields are very less, then we can also go for a coarse mesh there. Okay, so that is the basic idea, and whatever these solvers were offering is also the similar to that, because here the solvers are offering 2 things, like one is the adaptive meshing technology and another one is the manual control mesh. So this auto adaptive mesh control will help you to will help the engineer to automatically improve the mesh quality as per the field gradients wherever those are very high. Okay, so this automatically improves the accuracy levels generally. So if you can see the process of that one, generally it start with the initial mesh, and as per your convergence criteria, because as a design engineer we need to provide the convergence criteria. It will compute the fields for that particular initial mesh, and it will perform the error analysis, the energy error analysis we call it as. So that will define, okay, how basically whether it is this energy error criteria has met our requirement or not. If it is meeting the convergence criteria, then it automatically stops it. But if it is not meeting that convergence criteria, it automatically go back and refine the number of passes, which means that it automatically refine the number of elements. When I say refinement, means it improves the mesh element, mesh count generally. So that is the basic phenomena how this auto adaptive meshing technologies follows. But of course there are some always we need to understand that there are some limitations even on the meshing side as well, because there is an option called aspect ratios that has to be understand, like how much max you can able to go with this kind of meshing techniques or anything. And when you talk about finite, this finite element method, the first point comes into our mind is like how accurate when you're going for a finite element method. That also depends on how many number of elements you are considering and what sort of equations you are using it is. Whether it is a first order equations or a second order equations, that has to be defined. So generally in the case of Ansys solvers, specific to the specific to the electromagnetics point of view, we use just by default the second order mesh. But if you want to go back, yes, you can also go back to the first order element, which can reduce the computational time also. But generally, in the case of Ansys solvers, we will go with second order elements, which will improve the accuracy levels a bit. So in the case of 2D, it generally computes the triangle elements. It creates the triangle elements, and at each corner of the triangle, it computes the field quantities. And along with the corners, even in the middle also, it will compute the field quantities. But there are a couple of queries like how come you will address the internal part of the triangle. So that to address that, we have a polynomial equations, second order polynomial equations, which automatically address the inner part of the triangles. So basically, whatever the geometry it is, in the case of 2D, it will discretize into this multiple triangles, and this field quantities will be computed on sort of those triangles at corners and at the middle and even at the center. Whereas in the case of 3D, the same triangle will not be replicated, but it will replicate with the tetrahedrons. And even the tetrahedrons, so the similar application will happen at each leg. It computes at 3 corners. Okay, one is at the corners and even at the middle, and even the center part also going to be considered with the polynomial equations. So that's on the meshing side. But before that, like my colleague Manisha has mentioned, addressed a couple of things on the computational electromagnetics, and even we are also doing the same thing. But where exactly it's different. Okay, so that's where we need to understand what sort of applications we have it and how you can differentiate that. So before jumping into that, first we need to understand what is a high frequency and what is a low frequency, and where we need to use this terminologies. So if anybody comes from a DC, which means that the frequency is 0, and if it's going till certain megahertz range, that we will treat it as a low frequency range. Whereas, whereas in the other case, few applications which carries from kilohertz to the gigahertz and above that, okay, that will be treated as a high frequency ranges. Okay, so generally this as defined, as per the Ansys solvers, but there is no particular limit that you have to work only up to this. Okay, I mean, there is no particular thumb rule that you have to go only for 40-50 megahertz like that. There is a buffer is that. So how you can generally interpret by looking after a particular application, like how you can predict that. So that depends on the wavelength. Generally, if you have a higher wavelength, then the frequency would be the lesser. We can see here the wavelength is very high, whereas in this the wavelength is very less, which means the frequency is very high. It generally depicts the velocity of speed of a light. That defines general equations of this particular one. So actually, why we need to have these two? Okay, because to understand this Maxwell equations, okay, by Maxwell governing equations, it's difficult to address all sort of applications, okay, which are like a far field. Some of them are like far field, and some of them are near field, and few of them are like a component level simulations on the electromagnetic front. So generally, in the case of high frequency, what happened? It's a kind of data transfer might happen. Okay, whereas in the case of low frequency, it's a kind of power transfer will happen. Which means that you can see, if you take any examples like a motor or a generators or a transformers, there the power ratings are very huge and the frequency rating is very less compared with the high frequency range. Whereas in the case of high frequency applications, like you can take any electronic devices, they are operating at higher frequencies. And whatever the power rating or the voltage rating which are operated, those are at lower level. Okay, so that is the basic differences that needs to be understood. And according to those applications, we will choose the right set of solvers which is best suitable to handle that particular applications. And here is a simple applications like how we differentiate generally, like starting from a permanent magnet, where there is no point of talking about the electromagnets or anything. From there to time varying magnetic fields, generally we will treat as a low frequency. And whereas in the high frequency, the major sort of applications like antennas and even the PCBs, okay, the antenna placement and radars and crosstalks, so such kind of things comes out of the high frequency part. So if you talk about the on the sense of automobile part, the first part we need to understand is like the huge set of applications which can cover on the automobile applications from the computational electromagnetics. But honestly speaking, only computational electromagnetics will not solve the complete problem of that one. It needs a multi-physics environment. So here this is, I can say, generally like what sort of areas we used to cover in that actually. Okay, so that's where this it can be a traction motors or a fuel injection systems. It can be a starter motors or the actuation system which is required for this ABS braking. Okay, and the bus bar analysis which are nearby this electronic components, and the wireless power transfer, which is the, I can say, the a booming concept in the automotive sector. And even the if you are going for an EV vehicles, there it is the batteries, okay, and its ECU circuits, and the powertrain converter devices which are responsible for this harmonics part. Okay, that is also the create a major important role. And overall the electromagnetic sensors which are responsible for the speed or detecting some hall sensors or anything. So such kind of things will play a role here in the automobile applications. We will just see. So what I thought, like, I will just give you a brief on the methodology point of view, methodology point of view also, how generally people will consider these things. So in that sense, I thought of just giving you a brief on the motor point of view. Okay, so that is like, if you take a motor, generally where they will start is, they will start with some analytical calculations. Okay, and they will I'm sorry, they will start with some analytical calculations with some huge number of design variations. Then once they finalize the couple of designs out of huge number of design iterations, they will take it to the next level called high fidelity solvers. Okay, that's where this FEM solvers will comes into picture. Will comes into the picture. The finite element methodologies, and that will take it out to the next level, like the multiphysics environment, to understand the multiphysics challenges. And finally, you can also take those electromagnetic solvers to the the computational fluid dynamics analysis to the next level for the structural analysis, to understand the vibration behavior of the motor, or any it can be a motor, it can be any other components. So the same funda has going to be applicable for the remaining components, remaining electromagnetic components. But of course, there are slight differences, because analytical equations for all sort of applications is really difficult. So most of the times when there is a complex structures, they are going to start from the finite element method. So this is the complete comprehensive analysis for the motors part. And the CEM procedure, if you want to follow this, generally, like, we need a CAD geometry to do this computational electromagnetic model setup part. Okay, where either you can create a templates. Okay, because a couple of applications has already templates like motors and transformers. Okay, the electronic transformers, or toroidal structures, such kind of things has already pre-existing templates, which automatically helps you to create the geometry. Or otherwise, you can directly integrate your own CAD formats. And then once you import it, then you need to create a mesh for that particular creation. Means to assign a right set of mesh, and then assigning the materials part. And you have to consider the right set of boundaries. That is an important aspect in the pre-processing part. And once you've done the pre-processing part, then the next part is a solver, where automatically it will do the complete solving. But in the back end, it will run the Maxwell equations to help out, to get this particular field quantities. And first part, what it will do is, like, it will create a mesh out, in that particular geometry by doing the discretization of the geometries. And it will create a huge number of mesh elements, and that will be responsible for the complete field quantities. And while it is creating, it also needs to understand that whether it is converging or not. Okay, so that is part of solving. And if it is converging well, then it will help you with the field quantities. And once you finish the solver part, then the final part is the post processing, where you can able to extract the complete electromagnetic outcomes. Like, it can be a contours, which will tell us about the saturation plots of the particular steel material. It can be, or any sort of material it can be. Okay, so if you want to see the field quantities or saturation effects, so such kind of things you can able to see here. And the data table formats, it can be the XY plots, or you can say the field calculators, which helps you to write your own set of equations. So just to give a brief idea, because honestly speaking, out of all these applications of electromagnetics, I can say 70 to 80% of the market was captured by the motors. Okay, so if you want to really know that where exactly we are placing on the electromagnetic side, I can say, for an EV vehicle, you can start from an integrated starter motor or a generators, and starter, wiper motors. You can say the window lifting motors, and the seat adjustment motors, you can see, and the battery robust charging motors, and traction motor applications, and the motors which were used in the steering part, and even on the oil lubrications part. So there are multiple motors, I can say. I mean, set of motors are implemented in a vehicle itself. So now you can understand that what sort of level, or what sort of the priority the motor has currently in the market. So if you talk about on the computational electromagnetics point of view, as on the simulation point of view, you can solve this sort of applications. Like, it can be the motor part. Okay, motor efficiency, or a torque profiles as per the requirement, requirement from the customers, or even the power ratings. So all sort of things you can able to do it. And on the transformer front, okay, if you want to predict the dielectric behavior of the transformers, or the losses, it can be the core losses, the forces which are acting on the windings part, or any such kind of applications, you can also do it. It can be a power transformer, or it can be a distribution transformer, can be able to solve. Okay, and it has some sort of expert solvers, okay, where you can also use that expert solvers to build the electronic transformers. So such kind of electronic transformers. And if you want to see if you want to see not only the electromagnetics, if you are also looking for the thermal behavior or anything, such kind of things can also be doable by coupling this electromagnetics, or by coupling this computational electromagnetics with the structural side, or it's a computational fluid dynamics. And one more important topic is this wireless power transfer, which generally helps you to do the the booming concept in the EVM market currently, and which generally helps you to do the wireless power transfer without connections. And at the same time, this computational electromagnetics will help you that what if there is some misalignment in the transmitter or receiver coil. So such kind of things you can able to do it without doing any physical testing or anything. Okay, with the computer aided design itself, you can able to implement that. And couple of things on the speaker part are in the voice coil, which were equipped in this automotive vehicles, and even the bus bars which are running at some which are equipped with some faulty scenarios. Then how the nearby components are getting this induced voltages or anything. So such kind of phenomena you can able to simulate. It's the same thing we were replicating right now. Okay, the current densities on the bus bars and whether it is within the permissible limit or not. And even due to this heavy current, heavy currents or anything, what would be the stresses, thermal stresses, or it can be what would the temperature rise in that particular components. And because of the thermal stresses, is there any deformations? So such kind of phenomena can be doable with respect to the multiphysics environment. And the final one is the sensors, which can tell you that where I need to place a sensor. Okay, what would be the right location so that it can easily detect. For example, if I want to sense light, if you want to turn a light or anything, by using a Hall sensor also you can able to predict that. But where exactly the position of this Hall sensor, that is the key point. So that's this Ansys electromagnetic, I mean to say this computational fluid, electromagnetic solvers will help you out generally. And it's not about only the Hall sensors, even if there are some variable reluctance sensors, which generally depicts the speed of a vehicle. Okay, it understand the voltage profiles, and that will be converted, that will be decoded into the signals, and that will predict the what would be the speed of your vehicle. Either it can be a two-wheeler or a four-wheeler, whatever it can be, that you can able to do it using the cogging wheel sensors. And finally, the eddy current flow sensors, where if you want like predict, is there any chance of porosity somewhere, so that if you want to predict using this eddy current flow sensors, you can easily predict those things. So these are the couple of applications which you can easily handle in the automotive application. So with this, we would like to wrap up the session. And if anyone has any queries, please drop it in the chat box.
Thank you for the presentation, Mr. Hara Prasad. We'll just wait and see if we do get any questions, and we can get you all to reply to those questions. If any of you all have any questions, you all can drop it in the chat box and we'll have it answered. We'll wait for another 2 minutes and see if we do get any questions.
Definitely, Sharad.
Thank you. Okay, we don't have any questions as of now, Hara Prasad and Manisha. So I think we can close this session and bring it to an end.
Sure, Charlotte. Thanks for
Thank you.
connecting.
Thank you so much for you all joining in and giving us this insightful presentation. I'm sure the students will surely benefit out of this. Thank you so much for your time, Hara, Prasad, and Manisha. It was lovely having you both over here. Thank you so much. You have a good evening.
Yeah. Thank you, Cheryl. Thanks for your time. Have a great day.
Thank you. Bye.
Thank you, Sharon. Bye.